Welcome to qnawire.
So the allowed vibrational energy values for a diatomic molecule is given by, we've got E subscript V, which has our vibrational energy mode, is equal to H bar omega multiplied by the vibrational quantum number V plus a half. These are the allowed energy values. That vibrational quantum number has to be an integer, and as such, these values will be quantized. But we also know that omega can be written as the square root of the effective spring constant K over this quantity mu, which is the reduced mass. So let's rewrite out this sort of master equation of sorts. We have EV is equal to H bar, and then in brackets, V plus a half multiplied by K over mu. And finally, the equation for the reduced mass mu is given by the mass of the first atom multiplied by the mass of the second atom over the two masses added together. It's also given that our minimum amplitude will occur when we have V is equal to 0. And as such, we can allow E0 to be equal to a sort of analog to the elastic potential energy, which is E0 is equal to a half times by our spring constant, effective spring constant area K, multiplied by A squared, where A is our minimum amplitude, and this is the value that we are going to be trying to solve for. So equating those two together and setting V equals to 0 in this equation, we have something that looks a bit like this, and we're left with a factor of a half on each side, so we can cancel those. So that leaves us with this expression, and of course we can then solve for A. So we get, well, taking the K over to the other side and square rooting it, we get A is equal to root H bar over K times by mu, all to the power of a quarter. And this is because, obviously, root K divided by K is equal to 1 over root K, and then we square root it again to get this factor of a quarter. So now all we need to do is determine those values for the two molecules that we've been given. So let's start with the first one we were given, which is hydrogen iodide. So in order to determine mu, we need to know the atomic masses of both hydrogen and iodine. So I've looked up the masses of hydrogen and iodine in terms of the atomic mass unit U, which I've also written down there, the value of U. So what we need to do is sub that into our equation for the reduced mass. So mu is equal to, well, multiplying these two together, we get 1.0079 multiplied by 126.9 U squared over 1.0079 U plus 126.9 U. That will come out as 0.99996 U. So now all we need to do is substitute into our equation for the minimum amplitude. So A is equal to, well, we've got root H bar. So the value of H bar in joule seconds is 1.055 times 10 to the minus 34. And that's over our spring constant, which is given as 320 newtons per meter, multiplied by our reduced mass, which we've just worked out there, as 0.99996 U. So that will be 0.99996 times by the atomic mass unit, which is 1.66 times 10 to the minus 27 kilograms. Punching that into a calculator, it gives us 12.0 picometers. So doing the same thing for hydrogen fluoride, we need the atomic masses of both hydrogen and fluorine, which are given here. So the mass of hydrogen as before is 1.0079 U, and the atomic mass of fluorine is 18.9984 U. So again, plugging the numbers into our equation for the reduced mass U, using MH as M1 and MF as M2, or whichever way around you want, you end up with a reduced mass of 0.95712 times by the atomic mass unit U. So plugging into our equation for the minimum amplitude, we get A equals, again, root h bar, which is 1.055 times 10 to the minus 34 joule seconds. That's going to be all over our effective spring constant, which is 970 newtons per meter, multiplied by our reduced mass, which is 0.95712, times by our atomic mass unit, 1.66 times 10 to the minus 27 kilograms, giving us an answer of around 9.2 picometers.